Good morning, and thank you, Mr. Chairman, for introduction. I will talk about the ultimate limiting error sources in cell mixing interferometry. This work is done in cooperation between University of Pavia and Dayeh University in Taiwan. Okay, here is an outline of my talk. After introduction and motivation, I will spend very few words about cell mixing interferometry and some more words about speckle-pattern. Then I will discuss errors coming from a speckle-pattern. Then I will show results and I will go to conclusion. Okay, in interferometry, for example, in Michelson configuration, resolution is limited by photon fluctuation noise, and a very good noise equivalent displacement. Less of 1 picometer can be achieved, but with reasonable power levels, but this resolution can be reached with some effort after removal of other error sources coming, for example, from environment perturbation in pressure, temperature, leading to refractive index fluctuation. And other source of errors can be a residual mechanical instability of your setup. In a different interferometric configuration, for example, in cell mixing interferometry that is used mainly for its advantages over other setup. It is intrinsically non-invasive, no mirrors is needed. It can operate from rough surface, and this is a key point. It's self-aligning. It requires a very low part count in optics, and signal detection is very easy. You can use as the detector the internal power monitor photodiode, for example. Well, when we remove any other source of error coming from the environment or from mechanical vibration of the setup, in this case, if you use a rough surface as a target surface instead of a mirror, resolution is no more limited by a short noise of the photons, but you are limited by a speckle pattern. What is it? Okay, this is a typical cell mixing interferometry setup. We have the sources here, some optics. Often an objective is used to focus onto your target. Attenuator is usually needed to choose the right value of the C factor. I don't enter in details of cell mixing interferometry since it has been treated by other speakers before. And the signal can be, for example, detected from the real signal power monitor photodiode. Okay. Well, the target usually is rough. Okay, what does it mean, a rough surface? It means that instead of having a flat mirror-like surface, we have some structure in the surface, and the height, the difference between the actual shape of the surface and the average plane. It is a geometrical roughness with a correlation length in the target plane smaller than the wavelength of the light we are using, and it has a span along the line of sight of the interferometer higher than the wavelength. So you can treat each point, each correlation area at the target as an independent point source with, for example, same amplitude, but with a totally random phase. So if we look at the diffused light after laser beam illumination with a plane wave, we will see a speckle pattern that is some bright grains in the shape of figures, inside which we have coherence immersed in a dark background. How this happens? If we move away from a point of bright light, if we move away, we will see the source, the rough surface, and we see each individual source, with each of them with the random phases. We see them slightly different, with a slightly different phase. And so when we sum up all the contribution, we will have a decorrelation between the sum vectors. And the shape of these grains is different in the transversal plane and along the line of sight of the source, and the speckle grain size are shown here, and they depend on the ratio between distance and source diameter for the transversal side of the speckle, and it depends on the square root of this ratio for longitudinal size. Okay, and this light configuration, this speckle pattern gives some errors. Mainly it gives amplitude fading and a phase error. We can divide the error contribution coming from the speckle pattern into these two aspects of the speckle pattern: amplitude fading and phase error in the interferometric signal that had this typical expression. Amplitude fading is responsible of occasional signal loss, and if you have no signal, you can't measure anything. And so we can cure amplitude fading by some countermeasures, and some of them are listed here. We can use a super diffusion target. We can use an automatic gate control or high-pass filtering to remove baseline drift, or a bright speckle tracking. Once amplitude fading is cured, we are faced to a phase error. Okay, phase error is due to loss of coherence while you move through the speckle grain, or in the transversal direction or in the longitudinal direction. Okay. When during the displacement you approach the speckle sizes, you have an error of the order of a wavelength, plus or minus pi. In interferometry, we have to deal with longitudinal speckle size. Well, the noise equivalent distance, defined as a ratio of phase error variance to your scaling factor times the wave vector, is a measure of the phase error. And we can divide the analysis of the phase error due to speckle pattern into two groups. We can first speak about interspeckle error, that is when your displacement is within a speckle size, or intraspeckle error when your displacement is greater than your speckle size. Case 1 can be examined by speckle pattern statistics. Statistics of point statistics of a speckle pattern is summarized here. The field components, real part and imaginary part, oh, thank you, are independent random variables with circular Gaussian probability density function, and we have some other distribution for intensity and phase. What is important here is that the phase distribution is a uniform distribution over the full angle. So we have no information on distance phase. It is all error. Okay, by exploiting the joint statistics, I don't go into details here, joint statistics of intensity and phases at two different points during your measurement, during the measurement of your displacement, we can reduce the error. Okay. Just I comment some graphical results. What we can see here is that here we have a phase error, and here we have coherence between the 2 points of observation, and we see that we get a lower phase error if we choose to measure between points with intensity higher than mean intensity of the speckle pattern. Okay, here is a detail. And, well, I skip over the interspeckle case because I have no time, sorry. And I had also some simulation for some particular sort of source, but you can read this into the paper in the proceedings, and I go straight to conclusion, saying that we have shown that by proper exploitation of speckle pattern statistics, we can get interferometric measurement with resolution of the order of wavelength overspan up to a meter from diffusion target. Thank you for your patience.